Assalamu alaikum, good morning, good afternoon. Today, we plan to cover the third lecture of artificial lift technology. Today, the main topics will be around the reciprocating sucker rod pumping system, one of the main common used artificial lift worldwide, and one of the oldest type of artificial lift system. It's used since more than 7,000 years. If you look to the middle picture, this is coming from the old Egyptians, and it's the same concept of lifting fluids. Maybe technology changed, maybe just as a type, as a capacity, and so on. But all the idea, theory is the same. This type of artificial lift is mainly used for for wells. Some people said for shallow wells, low production, but currently with the technology is used for variety of different type of wells, maybe deep wells, high volume wells, and so on. We try to just to show you how come that from a system only used to lift fluid from just 1 meter, 2 meters, up to currently is used to lift fluid from 3,000 meters, or just we can say 17,000 feet, and so on. Our topics today will cover, our presentation will cover some introduction about the system, what are the main components for that system, I'll try just, to focus on surface and subsurface part, plus give you some hint about system design and 1 or 2 slides about system optimizations and how currently the system is optimized, the monitoring, and so on. What is a reciprocating sucker rod pumping lift? The reciprocating sucker rod pumping system, as the picture in front of you, this is a system is used in most type of oils or waters wells. It is the most common popular artificial lift system used worldwide. Currently, if you count by the number of wells, you found over 75, 76, or maybe more than that's the number of wells worldwide using this type of system. Yes, configuration in the surface downhole it changed, but same concept, the same techniques is reciprocating up and down. Then the sucker rod pumping system or reciprocating sucker rod pumping system, it's the most common used artificial lift worldwide. The number of wells, as I said, over 75, 76, maybe 78 percentage of the number of wells using this type of wells is spread all over the world, in North America, Latin America, in Middle East, in Far East, and so on, It's a system, what is reciprocating? It's a system using a surface pumping equipment, this is a surface, the one at the surface, using a surface pumping equipment just to rotate, is convert the rotation of what we call prime mover or motor, something like that, to a reciprocating, vertical reciprocating motion up and down. This is just to drive what? To drive a subsurface pump. It's running mechanically, because this pump running mechanically run by reciprocating action, reciprocating system. It's a positive displacement type of the mechanical pumps and so on, This system generally, in order to know why it is more people are used, why it's common used worldwide, why most of the people in the world, when we start to design the well, if they found the rod lift system can be lifted, the well they are using immediately, without thinking, if they found that, because this well can be used for most type of wells, most type of crude oils, it can be used for heavy, medium, light crude oil, you can use for heavy crude oil up to, I don't know, around 12, usually 12 API or just less, and used for crude oil, more than 45 API and so on. Sand, yes, if there is a sand, but, all that's, and gas the same, but all that needs some, some special design, especially if I start to use very heavy crude oil, then the downhole pumps, the downhole equipment should be selected to that condition. Sand is the same. If there is a well is sandy, they have to select the right downhole equipment to handle sand. But it can be used in some area, especially, for example, in Middle East, if the well stops, you found 2, 3 joints above the pumps is full with sand, That's mean the pumps is lifting very high quantity of sand. And so same of gas. Gas, what we mean, the very high gas ratio. All the background about this system, it's used only for shallow wells or just no gas or some, no, is it changed? Currently, this type of artificial lifts maybe also can be used for what we call unloadings or just deliquefied dewatering gas wells, That's mean, yes, can be used for a very high amount of gas. But how come? Let us, see, how we can use this pump for high gas ratio wells, for sandy wells, and so on, Even for the pressures, this wells doesn't care about bottom hole prong pressure. Since the fluid is reached to the downhole pumps levels, even it will be about 1-2 feet above the pump can lift it, that fluid, that fluid. Up to even the fluid level, even reach to the surface, is no problem, doesn't care of the pump. Is a reciprocating, positive displacement type of pump. How much volume they can lift it? Yes, they can lift it from 1 barrel to a day. You can adapt the system to lift even 1, 2, 3 barrels. There is, a lot of wells in state and some other area just lifting 5 barrels, 3 barrels, 4 barrels per day, and it can lift also up to 7,000 barrel fluid per day. If you look to in Canada and some other area, they are using this type of artificial lift to produce a very high volume, like 7,000. But each type or each volume for sure, from a certain depth, I cannot lift, for example, 7,000 barrel fluid per day from deep wells. No, it should be from shallow wells, because I am lifting this flow. Also, this type of artificial lift used for all type currently, due to technology in the road and the pump and the surface equipment, can use for vertical, horizontal, slant direction wells, even for horizontal, we can run the pump in the horizontal section. How come? Let me, walk you through the slides through the type of downhole equipment to see if this is possible or not, and how come we can produce from horizontal wells or very deviated wells, or the degradation severity is high, and so on. Even for hot fluid wells, if you look to most of the fields running under steam stimulations technology just to enhance the production, you found majority of them is using rod lift, reciprocating sucker rod lift system, and so on. This is just, the advantage of this type of the artificial, the application. Since this all type application, for sure, as I said, initially, when you start to design and selecting your artificial lift system, and you found the rod lift system can be capable to lift your wells, then go ahead and use it. Why? Because it's very economical to repair and service. All the repairing and service for this type of artificial lift, it's usually done in the field. You don't need to send your equipment to the supplier or the service company to repair and so on. It's a very easy, very cheap to repair and so on. And not only that, even the optimization, currently there is a very high tech in optimization control for this type of system for downhole and surface optimization. What? Optimization, the amount of fluid, optimization, the intake pressure, and all that you can optimize, and you can monitoring even, even from this monitoring and optimization control, you can monitoring how the pump is running downhole, how you can estimate it in a very good accuracy, the bottom hole pressure, the flow rates, and so on. It's a positive displacement type of pump. A strong drawdown can deplete the pressure or reducing the bottom hole pressure to a very, very low amount of pressure to allow the reservoir to give you the maximum potential of its reservoir according to the well productivity and so on. And also, this is a cheap downhole equipment system, and it's a very economical. It's easy, to upgrade and just the downhole materials. For example, if you selected downhole equipment to produce a wells, just sweet fluids, no water, high salinity water, no H2S, no CO2 as initially, and suddenly, or with time, we found this water start to have some corrosion environment. You can easy to upgrade downhole pumps, and the road is not costly. Most of the cost of this equipment in the surface equipment. more than 75% of the capital investment for the system from bottom to the surface in the surface equipment. And this front view, then that's mean the downhole equipment is only costing less than 25% of the total system cost. It's flexible, very flexible technology of artificial lift to meet with a change in well condition. The well condition other pressures, well condition other fluids, will condition at the amount of gas, increase, decrease, sand, and so on. Very flexible, just to adapt this technology. And even you can change the pumping parameter from the surface to meet or to match the well productivity, downhole, one of the good things for this is high system efficiency. I mentioned that before. The system efficiency, it's how much power I gained or how much power it's used from this system to how much power I just, running this system, how much horsepower I give to the system. For example, for the downhole pumps, in order to produce a certain volume of a fluid is required, for example, 10 horsepower. Then how much, horsepower I used as a surface equipment to drive all the system. If it's, for example, is 20 horsepower, then 10 over 20, that means the total system efficiency is 50%. This could be the second type of artificial lift, second type in system efficiency after the progressive cavity pumping system. The total system efficiency can be reached to 55, 60, 50, something like that, Not only that, also high salvage value, As I said, most of the equipment, most of the cost of the equipment in the surface equipment. And with the time, I know some wells running since more than, 50 years. Still the same surface equipment and not changed. And even if the well start to be completely depleted or watered out, and so you can use the same equipment to run another well and so on. And so then still the value of the equipment on it, with the time and so on. What are the system component? Yes, we said about application, we said about advantage. All of that should be known. What the component of the system, how the system is running and so on, If you look to that pictures in the left right side hand of you, this is a total system, from bottom to downhole. In the bottom equipment, we have downhole pumps. This is the heart of the system. The downhole pumps is the heart of the system, is a reciprocating up and down positive displacement type of pump. Plus something, to run the pump, to activate the pump, to connect the reciprocating motion of the surface equipment and to transfer to the downhole pump is called the sucker rod string. Sucker rod string is a mechanical link between the surface equipment and downhole equipment. That's it. Doing nothing, just this is the main function of that mechanical connection. Plus, how's running, how's lifting the fluid and so on. We'll see the rod lift system and so on. There's different type of rod lift system with a new technology. In the past and the old, we have only steel, just jointed rods and so on. Currently, we have some more time, what we call flexible, continuous rod and so on. It allows the system to run in different well geometry and so on. Plus the surface equipment. Even for the surface equipment, the main function of the surface equipment is, to produce a reciprocating motion, which is transferred to the downhole pump through the rod string. Yes, there is what we call the beam type rod lift system, and also vertical, vertical motion, vertical reciprocating rod lift system. This can be mechanical, can be hydraulic, and so on. But at the end, the surface equipment is just to produce a reciprocating up and down motion. This is the main three categories of the pump, plus the prime movers, which is drive all that system. Prime mover, we'll see later on. It can be, something to produce a rotating motion, It can be a motor, can be electric motor, can be engine drive by diesel, drive by gas, whatever type of you have. Plus the monitoring systems, well control and so on. And see. But the main four component of the system, if one of them is failed, the system will not working, is the subsurface downhole pumps, the sucker rod string, the surface pumping units, and the prime movers at the surface. Uh, Let us just, to go a little bit down in the wells and see, how this system is running the well, how this system I installed in the wells and so on. For all type of artificial lift or all type of production, even flowing wells, I have to know what type of well completion I have to run in the wells in order to produce this well. Flowing artificially, artificial is rod lift, ESP, PCP, and so on. Let us just, to have some general overview, not in details and so on, about the general sucker rod system completions. First part in completion is the tubing, the tubing string. Even if some wells, in some area in shallow wells, it's producing from the casing, but at least there's a conduit for the flow to move up and down. This tubing can be different type of, of tubing size, whatever, depend on the depths, depend on a lot of condition, while you can design this well. Second thing, I need to have something inside the completion. I need to have a certain piece of equipment just to run and to stop the pump, to install the subsurface pump on it in the completion surface in the well. This is called sitting nipple. The sitting nipple here is the main function, just to hold the subsurface pump in place while I design at what depth this should be. This is called the sitting nipple. And in some wells, maybe if the wells start depths to increase, we are using what we call tubing anchor catchers. Tubing anchor catcher is a device like a hydraulic, is like a backers. If you look to like a backer, but without rubbers, you will see what the function of the tubing anchor catcher for this one. Plus, after that, the wellhead. For sure, based on type of artificial lift, will be a special type of the wellhead. We'll try just, to go through all that pieces one by one in very simple way. Then the form component of the well completion for this artificial lift system is the production string, sitting nipple, tubing anchor catcher can be used or cannot be used, depend on the downhole condition and running parameters, plus the wellhead of this system. Let us, to see how we can run, what type of completion we have. If you have a shallow wells completion, remember I said, tubing anchor catcher can be used or cannot be used. For shallow wells, maybe I don't need to use what you call tubing anchor catcher. All what I need, this is a wells with the casing. I need to run the tubing string. With the tubing string, I need to run the sitting nipple. The sitting nipple, should be run at the design depths, at a certain depths or design depths, what I need to run. Then this is a very simple completion, nothing else, on these shallow wells. After that, we ran the pump on the rod string inside the well, and the pump stopped on the sitting nipple. This is a very simple completions anyone can do in the field. It's not, they do not have any very high tech or something like that, Tubing string plus sitting nipple, it's connecting to the tubing string and running the well to the designed depths. After that, we run the pump. Either we'll see the pump, if it's tubing pump or rod pump, inside this part of equipment. Then, what for a deep wells? This for shallow wells. For deep wells, we'll have the same completion, more piece of equipment with these completions. Why we have that and so on, and how it will be looks like in some wells. Remember, this is a reciprocating sucker rod pumping system. Reciprocating sucker rod pumping system means it's going up and going down, like this picture and the one. This is the downhole pumps, upstroke and down stroke. In the upstroke, while you are going up, there's a valve in the pump is closed. When the valve is closed, that's mean while you're going up, all the fluids of your be on the rod string, which is connecting the pump and lifting the fluid to the surface. What that mean, That's mean no fluids will be on the tubing. Then the tubing will be just tubing. Yes, there is a fluid, but the fluid is lifted. The valve is closed and lifted by the rod string. What's happening in the downstroke? While we are going down, this valve is open. Then all the fluid transfer to another valve is standing valve, what we call is stationary with the pump as not moving. That's mean all the fluid in this case transferred to the tubing. Then the tubing subject to two forces. In upstroke, there is no fluid. All the fluid forces or fluid load will be in the rod string. In the downstroke, all the fluid load will be on the pump. Then the tubing here can be, contracting and, contracting, stretching due to different loads. Then will be a movement in the tubing. In order to prevent this tubing movement, we need to use a piece of equipment like this. If you look here, to this picture in the right side one, what we have in the going down, the valve, bottom valve is closed. Then all the fluids inside the tubing will be on the full tubing size cross-section area. Then the tubing will be under tension in this case. While we are going up, this valve, the top valve is closed. Then the tubing string, the rod string is lifting the fluid. Then in the tubing here in the bottom, there is no fluid will be in the tubing. This valve will isolate all the fluids from the tubing because it's going up and closing. In this case, will be no fluid in the tubing. Then the tubing will be contract. You will see the tubing in the upstroke can be buckling like that. In the downstroke can be stretched like that. If you left the well is running like this, there will be a tendency of the rod string, to contact the tubing wall. Then will be a friction between rods and tubing. Metal to metal friction then will be eroded each other, and we can create a big problem for the rod and tubing, and it can be really have big problems and severe problem for that. In order to eliminating that tubing movement, we are anchoring what we mean. We are fixing the tubing with the casing. Then whatever you change the load from the tubing, the tubing will not load because the tubing will be fixed with the casing with a device, what we call tubing anchor catchers. Tubing anchor catcher connecting, just either below the sitting nipple or 1-2 joint above the sitting nipple, depending on well condition and the design and so on. And this it's prevent the tubing movement. This is the main function of the tubing anchor catcher. Then, in order to eliminate the tubing movement, we need to run tubing anchor catcher. Remember, this is a simple completion we said before. In this completion, as a difference than the shallow well completion, you have two pieces of equipment running on the completion. The setting nipple is the same. Plus, you run the tubing anchor catcher. If you are able to run the tubing anchor catcher below the tubing, but above the perforations, let's go ahead and do it. The tubing anchor catcher should be as near as possible to the setting nipple. The first choice for you to be a couple of joints below the setting nipple and so on. If you're not able, you can put about 2-3 joints above the setting nipple and so on. The design and criteria of the wells and the place while you are setting the tubing anchor catcher, it's is restricted you to see where is you can use this is a tubing anchor catcher, and then you run the pump inside that. This is what we call the well completion for medium or deep wells. Medium or deep wells, usually if you start to run below 3,000, 4,000 feet, maybe you will need that, and also depend on the pump size and so on, If we leave the tubing and without tubing anchor catcher, this is a picture of real pictures of the tubing from inside, and this is the road, while they are eroded, they friction to each other. See, in the left side one, the road is eroded, and consequently, the tubing is eroded. Then the tubing, it's is burst. Tubing is have a holes, and you can the production can be circulated through this hole and so on. Then tubing anchor catcher to reduce tubing movement and to reduce the road and tubing coupling wheels and so on, to prevent even the casing wheel, because if the tubing is movement and there is no big clearance between the tubing and the casing, and the coupling of the casing is big, then this can have some tendency for the coupling to erode it, to contact the casing. If the coupling is contact the casing metal to metal, maybe you damage the casing. This is also the coupling, real coupling from a well. After we did some failure analysis, we found this coupling, is eroded. If the coupling of the tubing eroded like that, means that casing also can be eroded and so on. Meanwhile, also increase the downhole pump efficiency because you're reducing the movement of the tubing and so on, and you increase what you call the downhole effective stroke to run the downhole pump. This is just general basics about the completion. There is some more things about that, but this is general. You will find, this is the main concept of the completions for rod lift system, either for shallow wells or for deep wells. Initially, when you start to design your well, you design the well without tubing anchor catcher and see how much tubing movement. If you found tubing movement, then you start to install tubing anchor catchers and you reevaluating the well. Not only that, since this type of artificial lift is very, very flexible, and even, sometimes some people, producing from more than one zone, and even this zone should be not producing commingly. Sometimes, you wanted to produce each zone separate than the other, you don't like because one zone was high pressure, one zone was low pressure, and so on, then some people, and I know some area and different area run with what you call selective completion, selective completion, then yes, the main concept here to run with a setting nipple is the top one, this. But after that, you have to run with certain device like what we have here, sliding sleeve, and in this case, we replace the tubing anchor catchers with the backers. With a backer, but this backer should be set under tension. When we set the backer, the tubing should be, this tension backer should be set the tubing under tension. There is a certain way, certain techniques, and so on. There is an SP paper I published about the well completion for rod lift system. If someone is required, that I can send to him, this paper is SPE and it's available, and so on, talking in detail about the well completion for rod lift system, But due to sake of time, we'll not go in details for this now. What other component? This is a completion. Then what are the main components for the system? The main component of the system, one of the main parts, or the initial parts, or some people say this is the heart of the system, is the subsurface pump. The subsurface pump, it is the heart of the system, really, If you design the pump very well and, you are taking all the consideration about what's going downholes, because this pump, it's handle your downhole flows, sandy, gassy, heavy viscosity, light viscosity, heavy crude oil, light crude oils, whatever you have. You run the pump is adequate to lifting that float without creating problem. Because if there is any problem in the downhole pump, this problem will transfer to the whole system, to the rod string and to the pumping units and even to the prime mover. Then you have to select carefully the downhole pump to lift your float based on that. In the market, yes, in the market, there is a variety of type of pump configuration or pump. It can be handle or running, your downhole condition, downhole floats, and so on, Then what are the main functions? Since like that, let us to talk, the pump can handle all type of float. Then what's the function of this pump? What this pump is doing, Usually the downhole pumps is doing two functions. Regardless of second rod or PCP or ESP or for surface pump, usually should do two functions downhole if it is artificially lift pump. First of all, to decrease the bottom hole flow pressures in order to allow the production to produce the desired, the target production from the reservoir. According to your inflow performance, you design to produce a certain volume of the well based on your productivity. Based on that, you must decreasing the bottom hole flow pressure to a certain value, But if you're decreasing the bottom hole to a certain value, then maybe the value of the bottom hole flow pressure, it's not high enough to lift the flow to the surface. Then this type of pump is, the second function of it is to increase again this bottom hole flow pressure to lift the fluid to the surface with the desired bottom hole flow pressure and overcome the pressure loss in the. Then the pumps make two functions. There is two functions for the pump, mainly two artificially pressures. One below the pump, it's a bottom hole flow pressure. Artificially, bottom hole flow pressure is decreasing to allow the formation give you the designed production. Plus, it's increasing again to a certain value of the pump, what you call is discharge pump or just a artificially a new bottom hole flow pressure above the pump to lift flow to the surface with the required bottom hole flow, required wellhead pressures to allow flow to reach to the separators or just to the surface facility. What are the main components? Remember when I said this type of artificial lift, it's using in more than 75% of the world due to it is very simple technique or very simple type of artificial lift. In order just to know how its simplicity of this one, let us to look to the pump, downhole pumps first. What are the main components of downhole pump? This downhole pump, as I said, is a reciprocating pump. This pump, it's have 5 main parts inside the pump. But if we start to divide the pump, we divide the pump to 2 main components. What we call the outside of the pump, the shield of the pump, what we call barrel assembly, the part you are seeing from outside, it's called barrel assembly when you see the pump. The part you not see inside the pump, we called plunger assembly. Then we have 2 parts, 2 main parts in the pump. The barrel assembly is the part when you are seeing, when you go to workshop or well site and have the pump outside and you look to the pump, you see the pump from outside. All what you see from outside, it is what we call barrel assembly. And all what you not see from inside the pump is called plunger assembly. But both should be working together. The plunger assembly is work inside the barrel assembly. Then the subsurface pump have 5 main components. One of the main part of the barrel assembly is the barrel itself. The barrel itself is a tube. It's just a tube. It's a pressure containing chambers. Is a tube, is a pressure containing chamber for the inside fluids and what we have and so on. Second part is what we be inside the pump, part from the plunger is called plunger assembly. Remember when we said this pump is a positive displacement, lifting fluid going up. When you are lifting fluid with this pump, usually you are lifting fluid against high pressures. If nothing, sealed this pressure to back again to down to the pump, then the fluid will be circulated around the pump. Then the plunger is provide what you call moving seal to carry what is a certain valve closing the upstroke to lift the fluid and so on, And this is valve was called traveling valves. Then we have plungers, have barrels, we have traveling valve. Traveling valve, it's just a valve. It's about ball, just normal ball plus seat. We can sit in the wall like these pictures, ball and seat, Inside a container, small containers of this, all that is called a valve. And this valve, it's considered like a one-way valve, check valves, can allow the fluid to go from bottom to the top and prevent fluid to go from the top to the bottom in order to prevent fluid to back again to the well, if the fluid is open the valve and go above the valve, it's not an easy the fluid to back to the valve unless this valve is damaged and so on. Same one in the barrel assembly called traveling valve. It's hold pressure during downstroke, inside the pump. Then you have 2 check valves in the pump. One stationary is standing valve, not moving. And one moving up and down with the plungers. I will show you the picture, how it's moving, how it's running all together, So it's called traveling valves and so on. Plus this pump, we said, it will run inside the completion, inside the sitting nipple. How to stop the pump inside the sitting nipple? How to prevent the fluid going out of the pump to back again to the bottom of the well. Then what you call sitting assembly, to hold the pump in place and to not allow the flow the pump produce inside the tubing to back again to the below the pump. These are 5 main components of the subsurface pump. Okay, how it's running all together. We said there is 5 main components. These 5 main components, how it work, how to interact to each other to produce the fluids. What's the principle of operation for this pump? Let us to go one by one. Let us to go while we're going up and while we're going down. How the fluids move from below the pump to the above the pump, from below the pump, from the perforation and so to the above the pump to inside the tubing and so on, Going up, we named this is upstroke. This is subsurface pump, is at the bottom of the well, the lowest part in the road lift system component. Then going up, we named this upstroke. Remember, I said the pump have two main parts, barrel assembly and plunger assembly, plus have 5 main parts: standing valve, traveling valve, plunger assembly, barrel assembly. Going up, what mean, if you are going up, that's mean, all the fluid will be act on the top valve, the moving valve, the traveling valve. If the fluid act on the top of the valve is a ball and seat, then this fluid will be closing the valve. If this valve will be closed, then the pump, while going up, will displace all the fluid above the plungers, above the traveling valve. It will displace to go out of the pump to be inside the tubing. The tubing just connecting immediately above the pump. Then all the fluid here while going up, since we are going up, all the fluid, since this valve, traveling valve is closed, will displace this fluid going up because there is no place. Is moving is a positive displacement. It's just, displace whatever they have in front of it, then displace all that fluid to inside the tubing. At the end, we say that's complete the upstroke. This is going up. Then while the pump is going up, what happened downhole? What happened in the bottom of the pump? Because we said that you have two check valves, Usually the check valve is opened by delta B. If the pressure below the valve is high, then the valve is open. If the pressure above the valve is high, then the valve is closed. Since this valve is closed as soon as it starts to going up, then when we are going up, they left an empty chambers, empty volume below it. This empty volume and isolated the pressure inside the tubing from below the traveling valve. That means the pressure inside the chamber of the pump will be a low. Then the pressure below the standing valve is the intake pressure, or the bottom hole flowing pressure, for sure will be higher than the pressure inside the pump, because there will be no pressure inside the pump. In this case, this traveling standing valve will be open. Then in the upstroke, while the standing valve is going up, displace the fluid above it. In the meanwhile, the standing valve, it will be open, and it's allow for a new fluid to move inside the pump below the traveling valve. Then at the end of the upstroke, completion of the upstroke, that I displaced all the fluid already previously found inside the pump, and I allow a new fluid to enter the pump. This is an upstroke. What's going in downstroke? Then this is one in one direction. While we're going in downstroke, what happened? As soon as you are going in downstroke, this is ball. This have a certain weight of the ball. Then you change the direction of the fluid. You try to change the direction of the fluid below the pump. As soon as you're going up, the bottom valve, the standing valve, will be closed. Since the bottom valve will be closed, the area between, or the volume between traveling valve and standing valve will be trapped. And if you have fluid in that, if you have incompressible fluid and so on, then the pressure inside the pump will start to be building up, start to be increased. As soon as that pressure increasing, even with 1 psi, with a pressure higher than the hydrostatic head or the pressure above the pump, traveling valve will be open. Then traveling valve will be open, and meanwhile, in this case, the fluid below the traveling valve will be displaced as soon as the traveling valve start to move down. Then start the traveling valve moving down while it's open. Then all the fluid already entered to the pump is moving to the above the pump, and will back to the same situation for the first configuration of the pump. In this case, you have a new fluid, and above the traveling valve, above the plungers, and the cycle will be repeated. Cycle will repeat. All this cycle we called one stroke. The one stroke, it's mean 50% of this stroke is going up, 50% in the time of this stroke is going down. This is a pump cycle, completely pump cycle. In order to understand how these valves is closed and how is operation, I put here in different ways. So in a pressure in terms of pressures and so on, in order just, to have some more, just some more information about what's going on the pumps and so on, see in the right side hand, in the left side hand is animation of the pump house running, and in the right side hand it is a two part of the pump, one in the upstroke and one in the downstroke. While we are going, in the very right side one, while we are going in the upstroke, the pressure above, it's what we call discharge pressures, is equal the hydrostatic head for all the fluid from the pump dips up to the surface, plus the wellhead pressures, plus the pressure loss. Remember in my first lecture, I say in order the well to be flowing, then the bottom hole flowing pressure should be equal that. In this case, I created artificially bottom hole flowing pressure. This is what we have in the top of the pump. What we have below the pump, below the other pump at the bottom of the pump, I have a standing valve. This standing valve, the delta B across the standing valve here will be the bottom of below the standing valve will be in pump intake pressure or bottom hole flowing pressure. But the pressure, above this traveling valve or just standing valve will be no pressure, because here traveling valve is closed. Since it's closed, it's isolated all this discharge pressure from the top of the standing valve. Then this allows the valve to open and, have a new fluid and so on. In the downstroke, as soon as you are going down, the ball or the valve change direction of fluid, this valve will be closed. This valve will going against closed volume, closed area. Then the pressure here below the traveling valve will be compressed, the fluid below it. And in this case, the pressure will be a little bit higher than the discharge pressure. Then the pump is, the valve is open. This is the animation just to show you how it's running. The bottom one is standing valve. Traveling valve here is going up, but traveling valve close. Meanwhile, standing valve is open, amount flows going down, traveling valve is open, standing valve is closed. Just to make sure about you understand how the pump is set inside the tubing, there is depend on depth of the pump, type of fluids, downhole condition, if I have sand, if I have a hot downhole in fluid, hot and full fluid, and so on. There's different variety of the bottom of the pump, just can be connected to the bottom of the pump in order to set the pump at any setting nipple or at any place downhole in the well. One of the good things of this type of artificial lift, in case you wanted to test the flowing wells and there is no setting nipple, there is a variety of technique or system you can use, like this one, what you call insert pump anchor, which you can connecting to the top of the pump. Insert pump anchor is a mechanical Baker J-slot type. You can connecting to the bottom of the pump, run the pump inside the tubing. If the tubing there is have no setting nipple, you can sit at any place, at any depth. You can test the well and you know what's going in. Or even if there is some damage in the setting nipple and so on, you didn't need to run a workover and so on, you can use. This just gives you some picture about, what type of setting device of the pump inside the tubing. This is just, to show you how it's sitting, this setting nipple, and this is a pump setting assembly, the setting assembly going inside the setting nipple, and this is, stop the pump and seal the flow. I put just this picture just, to have some imagine about that. Okay, this system we say, it's a forgiving system. It's a flexible system. And, there is a variety you can use, as I said, you can use in different type of wells, as a fluids, as a geometry, at all condition. Why? Because in the market, there is different type of downhole configurations. You can find the pump, it's which you suit your well, suitable to your wells, and so on, Generally speaking, according to the API, classification, there is two main type of the pump. One was called the tubing pump, and the other one called insert or rod pump. From the name of these two pumps, you can understand what's mean by tubing pump, what's mean by insert pump. If I say the tubing pump, that's mean a part of the pump, it's a part of the tubing. Remember, initially I said the pump have two main parts, barrel assembly and plunger assembly. In case of tubing pump, all the outside parts of the pumps is connecting to the tubing, what we call pump barrels and so on. For that reason, it's called tubing pump. The plunger assembly you can run on the road and so on. But for insert pump, the whole pump, barrel assembly plus plunger assembly, you can connecting to the road and you run inside that tubing and you are stopped as a sitting nipple inside that. This is just some animation about, how the tubing pump is run and so on. Usually we set the pump, we have plunger assembly and we have barrel assembly. But in case of tubing pump, the whole parts of the barrel assembly, except, the standing valve, it's connecting to the tubing, connecting to the tubing and run with the tubing with a well completion. And how is run? In this case, we run separate the standing valve and the plunger. We have different option, either to run standing valve like this from the surface by drop from surface or wireline operation, or you can connecting to the traveling valve assembly, the plunger assembly, and when you reach to the bottom of the well, you can dismantle this and so on. Plus, after that, you run the plunger assembly on the rod string, and the pump can run up and down and so on. The second part of the pump is what we call insert pump. In this case, the insert pump, the whole type of pump, plunger assembly, barrel assembly, standing, traveling, all pumps, the whole parts of the pump run as a one piece and connecting to the rod string and running inside the tubing and sit on the setting nipple. This is a well completion, have only setting nipple, no pump barrels, nothing inside it, only setting nipple, and then you connect the pump with the rod string and you run all the pump inside the tubing and you sit in the setting nipple. Even, as I tell you again, due to flexibility of these pump conditions and so on, even this pump have two different, have two different configuration. Either this pump can be, run the whole pump to be in the top of setting nipple, or the whole pump can be in the bottom of the setting nipple. This is what we call two different. Remember, I said this pump currently can use for sandy wells, for some other environment. Then you have to run the pump just suitable for this condition. For that reason, the manufacturing introducing different pump configuration, different pump geometry, and so on. One of them is called, top anchor pump. In the top anchor pumps, all the setting assembly in the top of the pump. Since all the setting assembly in the top of the pump, then the whole pump is run inside the tubing and pass from the setting nipple and stopped at the top of the pump. Then all the pump barrel assembly is passed from setting nipple. Plus, we have the second part is called bottom anchor pump. All this setting assembly in the bottom of the pump. Each type of this pump have some advantage and disadvantage. Let us to look if you have a sand. What of them you need you have to use? Either to use a bottom anchor or top anchor pump. If I have a sand and I'm producing a sand from these wells, remember the sand, it's have a tendency to settle down in the wells, If I start to produce sand with a fluid with this bottom anchor pump, and the sand produce, and for any reason and so on, the amount of fluid is not very high, the velocity of fluid is not very high, the fluid viscosity also, it's not high. You're using API, 30, 32, 33, 40, and so on, and even if the fluid is a little bit viscous and so on, and you stop the well for any reason, then the sand in the fluid will, if you well stopped or just the fluid, as I said, carrying capacity of the fluid is not high, the sand will settle down and will settle in the area between the barrels and the tubing in this area. If the sand start to accumulate in this area, the pump will become stuck. In case you have any problem with the pump, you will not be able to remove the pump from the well unless you remove the whole completion, and this will be big math, really big problems to have that. Then this type of bottom anchor pump is not suitable if you have a sand and so on. Then in this case, we are going to top anchor pump. But why since the top anchor pump is using for sand, why are not using for all the wells? No, sometimes, if you look to the top anchor pump, what's happened? What's the different pressure inside the pump and outside the pump? For deep wells, for example, wells with 10,000 feet, 8,000 feet, 9,000 feet, and you have a pressure of the fluid, discharge pressure of the pump, or just in the downstroke, inside the pump, while we are trying to open the standing valve. This pressure will be higher than the hydrostatic head. This pressure can be around 3,000, 4,000 psi. What the pressure will be outside these pump barrels, The pressure outside the pump barrel is a pump intake pressure. And usually the rod lift system use very low bottom hole flow pressure wells, can be 50 psi, 100 psi, 20 psi, 30 psi. Then you have a big delta B across the barrels in the downstroke, The big delta B of the barrel across the downstroke, then the barrel can be start to be, have some ballooning effect, and even sometimes can be reached to burst the barrel and so on, And this case is not, is not found in the other one, because the pressure inside and outside and downstroke will be equal, the same, and so on, unless, you have in the upstroke, the pressure outside will be higher than inside, but the collapse resistance is higher than the, the burst pressure, and so on. There is some different, more application, more function for each type, but however, this is, it's in the market and so on. In the market, not only, different type of pumps and so on, even different size. You can have found a very small size of pump from 1 to 5 inches pump size. You can find pump up to 4¼ inches, maybe bigger than this pump with a special pump. If you look to the pump, the normal size of pump, you found the incremental between one pump to the other about 1/4 inches of pump. These are pump pores about the pump. And when the pump size was increased, then the volume you required with each stroke, volume of this flow displaced to the pump will be increased, and so on. As I said, there is different type of pump. There's a tubing pump, there's a rod pump, and even there is a special pump, either special tubing pump, special rod pump, and so on, to handle your downhole condition, your difficult fluids you found in the wells, and so on. That's mean, what type of pump you need to use, what type of pump you have to use, how to specify the pump, If you wanted to specify the pump and order your pump and design the pump, how you are describe your pump. In order to describe your pump, the API supported us and helps us in that. He said, okay, in order to describe your pump, there is a certain description as per API to describe the pump, while all of us, we can understand that. If I send a certain description to an engineer in state, or engineer in Middle East, engineer in Russia, and so on, he understands what's the main component of the pump, what's the size of the pump. Is the top hole down or bottom hole down? It is a tubing pump or rod pump, and so on, Then the API creates certain descriptions, and all the people worldwide agree about this description and understand this description. When they read that description, they understand what this pump. What this pump as what? As a configurations and as a size, not as a metallurgy. We like to remember that. The API configuration of the pump is about the size of the pump and the configuration of the pump. Then the pump designation is the main part of what we call API specification 11. If you look or search about API specification 11AX, will give you a complete description about each part for the pump and what size of the pump, what's the configuration, what's the descriptions, and so on. This describes the main specification of the subsurface pump, and tubing pump and insert pump. Usually it's comprised of even different part, seven main separate categories. We said we run this pump inside the tubing. What if I design the pump, and when I start to run inside the tubing, and this pump will be not able to run inside the tubing? In this case, I failed to run. I spent a lot of money for workover, and I failed to run. Then The first description, you have to describe this pump will run in what size of tubing. Then I have to describe, I have to mention what tubing will be used in the well, and this pump to be run either inside or as a tubing. Then the first two numbers or first two parts is the nominal tubing size. API give us some, some descriptions about if tubing is 278, I use what number. If 3.5, I use what number. Usually use the nominal inside diameter of the tubing. The second three parts or three numbers is the plunger size, the pump size. Usually the pump size referred to the plunger size. What is the pump size? It is 1 inches or 2 inches or 2.5 inches or 2.25 inches. Usually you remove the segments in the middles, and you are added the three categories. For example, if it's 1.25 inch pump, it's 1.25. You remove the point is 125. Then if I said this is tubing is 20, that's mean tubing is 238. If I said it's 25, there is some table, just is give you the exact number. 25, that means this tubing is 278. Is 30, that means tubing it's 3.5 inch tubing and so on. The second part, it's the pump pores, plunger size. If I said, this pump is 2.25 inch, that's mean, I have to put the number 225. If this pump is 2 inches, then I have to put 200, okay? After that, remember I said I have a tubing pump, I have a rod pump, I have this pump, is connecting from the bottom, connecting from the top, and so on. Then the other four numbers or four letters after that is refer to the type of the pump and location of the setting assembly. It's a letter code. The first two parts is number code. This part is a letter code. For example, if rod will be R, if tubing will be T. There is a table, as I said, an API. If someone is needed, I can send it to you. Exactly give you what that mean for each part of this one. If the barrel of the pump, it's thick, this metal of this pump is thick while the pressure is high or something like that, then we call it heavy H or W thin and so on. If the pump is connecting from the bottom or the top, A is the top, B is the bottom, and so on, rod type, heavy walls, it's sitting nipple. And if the pump sitting assembly, it's cup or just all metal to metal, mechanical and so on. After that, what length of the barrel? If this barrel is 10 feet or 20 feet or 15 feet, or based on the manufacturing business, there is some standard for this one. The same for plungers, Plunger, it's what length of the plunger in feet, is 4 feet or 3 feet or other feet. Plus, there is some other two categories only used if the pump is heavy walls and, there is special connection is in the top of the pump. Let me give you an example just to clarify this a little bit more, just to make sure about you understand this well. This is a pump, what we have in front of us. This is insert pump, and this pump will run inside the tubing. This tubing is 278 inch tubing. The pump diameter, the plunger diameter or inside diameter of the pump is 1.5 inch pump. It's insert pump. You see these two categories, all the pump will run inside the tubing. The pump barrel, this barrel, it's heavy wall. See this picture, thickness of the barrel, as a steel. The right one is heavy, the left one is thin wall, It's heavy wall. Is a pump connecting from the bottom? You see the bottom assembly, setting assembly at the bottom, or at the top is bottom pump. If this pump is mechanical or just cup types, what is the length of the barrel and so on. If we give you this description, 25, 150, RHPC 12532. That's mean 25, it is the tubing itself, it's 278, and 150, that's the pump, it is 1.5 inch pump. After that, it's insert pump. You see, all the pump, it's run inside the tubing. It's insert pump. You can run the pump inside the tubing, it's insert pump like this. It's not a tubing pump. After that, we say, the barrel length. 12, it is a barrel length. From here to here is the barrel length. After that, the plunger length. 5 is the plunger length. What's the length of the plunger? Is 5 feet. The barrel is 12 feet. After that, the top extension, 3 feet, and the bottom extension is 2 feet. This is just an example, to show you how. But if you go to the ABI 11X, we'll give you a complete description about that and very easy to understand them. All the pump, what we have, it can be standard pump, or, it can be, special pump. In the market, there is a variety, plenty of type of pump, depends on your condition, If you have the gas, if you have the sand, you have the gas plus sand, you have the corrosions, if you have deep wells, if you have high volume, have low volumes, whatever you have, and there is different type of pumps. And if you have steam injection and so on. Second part in the, or just as a component of the sucker rod string, it is what we call sucker rod string, in the reciprocating pumping system component. Sucker rod string, it is a mechanical link. Mechanical link to connect the bottom of the bottom pump, the downhole pumps, to the surface equipment. This is one of the main functions. But usually the sucker rod string is not only transfer the motion, the reciprocating motion from top to the bottom. We have to consider while we design this that it's subject to what? To cyclic loads. In the upstroke will be a load because you are lifting the plunger and lifting the float. Will be a load in the rod string. In downstroke will be no load in the rod string. Then there is cyclic loads in this one. Also, this rod is a steel. There is some different type of rod, subject to corrosion environment. If there is water, sour gas, whatever, this rod string, is connecting to each other by what you call coupling and so on. There is some friction, can be especially for deviated well and so on. This can be also coupling restrict fluid and so on. All that you have to be considered in the design of the system and so on. It's just the normal standard one is a jointed sucker rod connecting to each other until I reach to the surface with a standard lengths, standard sizes. For this, usually the common standard length is 25 feet, and there is some rods with 30 feet. These are mean two common API standards rod string lengths, either it's 25 feet or 30 feet and so on. There's different type of rod string, jointed rod string, like the one what I show you before, like this one is jointed rod string, or we have what you call continuous rod string and so on. Even the jointed rod string, there is different standard type, there is different conventional, can be API, or there is non-API, because according to API, each rod have a certain grade can be also stand certain loads and so on, or there is something that we call, fiberglass. You remember there is some wells that run for deep wells, and if I start to run steel rods, maybe the load will be heavy, there is a corrosion, they are using fiberglass and so on, or hollow rods. Sometimes I need to use the rods just, to do some injection downhole, and so some people use hollow rods. And in the markets currently, there is what you call continuous rod, only jointed, only one piece of joint run from top to the bottom without coupling, without anything, is a little bit flexible, allow you to run in different well geometry, different well deviations and so on, and also eliminated the coupling and the rods, the shoulder of the coupling and so on. What are the main components of the rod string? If you look here, the rod string from the bottom of the pump up to the surface unit, whatever is connecting surface unit up to the bottom of the pump is called rod string. What are the main components of the rod string? What's comprised of the rod string? The rod string composed of polished rod. Polished rod is the first top part, which, connecting the pumping unit to the rod string, what's going up and down in this one. Plus some small rod string, which you can complete the wells, plus the rod string itself and the coupling, which is connecting the string and so on. As a general API dimension, as I said, is available 25 or 30 feet lengths, All the road is male-to-male connections like this, Plus, we have the coupling to connect the roads to each other is female-to-female connection. Usually, the road string size, it's starting from 5/8 inches with incremental of 1/8 inches until it reaches, 1.5 inches or just 1/8 inches, But however, in the market, the main common used size is 3/4, 7/8, 1 inches, 1/8 inches, Then the common size and the API size of roads, we have the difference between side and the other with incremental of 1/8 inches. For example, 3/4, second one is 7/8, third one is 1 inches, after then is 1 and 1/8 inches, and so on. And we have some small road string just used for lifting the pump, for completing the well, and so on, It's called bony roads. According to the API, like the tubing, like the casing, there is some different grade. As the API, there is 3 main grades, either grade C or grade K and grade D. There is different type of grade D and so on. And plus, there is some non-API special high strength load, which can be withstand high loads. High loads, it can be run for deep wells or big pore size pump if the standard API road string not able to lift the fluids and so on. In additional to that, sometimes, at the part of the road string, this road string, while we're going up, is lifting all the type of fluids, Lifting all the type of fluids in the road string will be under tension. While we are going down, the road string lifting nothing and going against, pushing the plunger inside what is a bump and so on. And there is a buoyancy also lifting that's, against this fluid. Then the road can be subject to buckling. In this case, in order to eliminating buckling, they are using a heavyweight bar. It's just big bore sides of steel rods or whatever, called sinker bar. The main function of that sinker bar, just to help the road string to be under tension and reducing, road buckling tendency of this one. The one of the advantage or disadvantage of this, it's, it's more weights on the road string and so on. But, when we design the wells, I have to consider this buckling tendency. After I design the wells, selecting the road string, I start to, to examine for a buckling. If I found a buckling for the road string, then I start to add 1 by 1 sinker bar at the bottom to keep the road string under tension in the downstroke and so on. In the market also, there is what we call fiberglass road, not only steel roads, fiberglass road. The fiberglass road is a lighter road string than the standard roads, which we allow you to run in a deep wells and so on. It's also suitable for corrosion, but the problem of this one, it's one of the advantage is cost. Cost is very high. Handling also, and also, it's due to excessive stretch or characterization of this fiberglass. Maybe I lose downhole stroke. There will be a more stretch on. It's have some problem. If the road is damaged for fishing operation and so on to fish this one, and usually fishing operation start to be very hard for fiberglass road. It's not commonly used and so. However, there is another type of roads is called, hollow sucker road, while I can use, to inject something inside the tubing, but this one usually used not for deep wells and for shallow wells in case I need to inject something inside the wells and so on. Regarding the more technology, the current technology used is called what continuous sucker rod. Usually we said the connected jointed standard roads is a jointed road with a length of 25 feet or 30 feet. Then each 25 feet or 30 feet, you have to use a coupling to connect to each other. This coupling, if you have roads, for example, size 1 inch, the coupling usually is more than 2 inches size. Then the coupling is restricted the flow. The coupling will run inside the tubing. There will be tendency of the coupling to connect with the tube to just to have friction with the coupling of the tubing and to already to each other. Then the manufacturing, introduced to the market what we call continuous rod, one joint from top to the bottom, eliminated all that's, coupling and all that's restriction is found. Plus, it's a little bit flexible, for bending and so on. But in this case, I have to have a bottom special device in case I have a problem and so on in the rod string. Then I have to shear and cut in the bottom and lift it to the surface. One of the main advantage, for the continuous rod string, remember, I said this can be used, allows the rod string, the reciprocating rod string to run for deviated well and even for horizontal well. If you look to the left, the right side hand, top one picture is a standard rod string with a coupling. See a deviated well, the coupling is running in the low side. Then the coupling, all the loads will be on the 2 points. The 2 point is contact between the rod string and the tubing, because the coupling have a big size. Then the contact will be only in the 2 point. Then the side loads, if you have a side loads here, then the side load will be in 2 points. If the side load, for example, it's 100 pound, then this point is subject to 50 pound up and down as a friction between rod and tubing, and the lower part also is subject to 50 pounds. Then the friction between rod and tubing with a side load is 50 pound forces in this one. What if I used a continuous rod string, the continuous rod string, and will be in the low side, then all that side loads will be distributed to all the rod string. If the rod string is, for example, the length is 25 feet, then all the 100 side loads is distributed to 25 feet. Then in each point of this one will be subject to only 4 pounds. Then each point, instead to be subject here 2.4, 50 pounds, each point here will be subject to only 4 pounds or something like that, over this point. Then the running life for the rod, running life for the tubing will be extended, for long times and so on. After that, even if there is no continuous rods and I run in a deviated wells and so on, what I can use to extend it, my rod life, my running life of the rod string. Usually they are using what we call a rod guide centralized, it's used just, to protect the tubing from the casing, for the tubing itself, for the rod itself, I inserting something like that is from a special hard, what you call special hard type of Teflon, nylons, plastic, different type, which is softer than the metals. If there is some erosion, will be in this part and so on. Sucker rod API nomenclature, as per also as the rod string, as the downhole pump, there is a certain nomenclature, the same for the rod string. Also, it's the same. There is API also defined the rod string at a certain nomenclature. If I run in the well rod string, what size of rod string I have to set according to the API. As I said, the rod string, according to the API, they define the rod string with a number. If I have in the well, a rod is 3/4 inches, they not say 3/4 inches. They said I have 6, I have 8, I have 7, I have 10. What does that mean, Because if you look to the rod string, I said it was incremental for each size between side, and the other was 1/8 of inches, The same, the bottom line of this one is the same, Then the incremental of this one is 1/8 of inches. Then 3/4 inches means 6/8. 1 inches mean 8/8. Then if you talk to the top parts of this decimal, then that's mean, 3/4 is referred to the number of 6. 1 inches is referred to the number of 8. Then the API define the rod string with a number and so on. Why is doing that? Because in majority of the wells, you run in the wells not only one size of rod string. Usually you run rod string with a tapered rod string. tapered rod string. That's mean why? Because in the top of the well, the rod string is subject to the highest load because it's lifting all the float of the weight, the weight of the float, plus lifting the weight of itself. What about the joint above the pump? The joint of the rod above the pump is only lifting the float. Then in order just, to reduce the weight of the rod string, and also as economical point of view, to reduce the size of the rod string, which will be more cheaper, then they ran with a tapered rod string from top to the bottom. In order to define this taper, then they define with a number. What that mean, and so on, and how we can have a tapered rod string. Tapered rod, that's mean the rod from top to the bottom is not one size. I run with a bigger size near to the surface. Then while I'm going down in the well, I have to reduce the size because the top part of the rod is lifting all the rod string below it. The top joint here is lifting the whole joint of the rod string plus the weight of the rod. But the lower part of the rod string only is lifting the float loads and so on. Then the tapered rod string is referred to the diameter of the largest rod while it is used at the surface of the well to the smallest rod size while it's used at the bottom of the well. And there is a special design, and there is different software used to just, to design this one in order to give you a balance about what size I have to use, what's the length of the top one, what's the length of the middle, what's the length of the bottom one, and so and so on. Then each size of the rod, as I mentioned before, according to the API, is give a nomenclature for each size of the rod with a certain number. 5/8 is the number 5. 3/4 number 6 was 6/8. 7/8 is 7. 1 inch is 8/8 is 8. 1 and 1/8, 1/8 of inches, 9/8 is 9 and 10 and so on. Usually, if you have a rod string like this, you have to refer to the first one and last one. And, logic will be a middle rods between the two sides and so on. For example, in the front of us, we have 3 sizes, tapered rod string, 1 inches, 7/8, and 3/4. According to the API, this one is referred, is called API 86 tapered rod string. When you are reading the book, or when you are reading the report, or the well report, or whatever, or someone say, okay, I have in this well API rod string 86. Immediately it should come to your mind that's 86 years means that you run in the top is 8 inches, 1 inches, in the bottom is 3/4 inches, then in the middle for sure will be a 7/8 of inches. This is what you call 86 tapered rod string. What if I run with one size from top to the bottom? If it's run with one size from top to the bottom, you repeated the number. Because according to the API number, the rod string must have 2 numbers, Then, for example, if I run from top to the bottom with 7/8 inches rod, then this will mean 77 rod string inside the well. If it's only 2 sizes, 7/8 and 3/4, then 76, and so on, But, according to the API design, according to the software design, I cannot say this is a tapered rod string API 86 rod string unless, this rod string is balancing with the stress at the top for each sections. The top, for example, if this rod subject to stress 90% of each maximum stress, the 87 is the 7/8, rod string, the top of 7/8 should have the same 90%. You should have the same 90% of each allowable rod strength, and so on. Come to the surface equipment. Surface equipment is very easy, and the function of the surface equipment only to produce a reciprocating motion, which transfers through the rod string to the downhole pumps. Mainly, we have the pumping units plus the prime mover in this one. the pumping units in the surface, which is, as I say, is producing a reciprocating motion up and down, is used to stroke the bottom hole pump, and also meanwhile to reduce the speed of the prime mover to the desired speed. Okay, the prime movers or the motor is running, for example, 1,000 RPM, but I need to run this well up and down with 1 RPM, with 1 stroke per minute, going up and down, or 2. How to do that? Pumping units with some other accessories is used to do then. It's carrying all the way to the float, not only, is reciprocating. It's reciprocating with carrying the well float, carrying the float of the rod string, the weight of the rod string, plus the weight of the float. According to the API also, API defined everything in the reciprocating rod lift system. Downhole pumps, there is API nomenclature, rod string, and the pumping units even the same. The beam type of pumping unit is the same. The API is defined the beam pumping type, this type of pumping unit, because there is different type of pumping unit, different geometry, different capacity of these pumping units, because according to the well float, the load floats, the float volumes, and so on, I have to use a certain side of the pump, According to the API is defined the pump with nomenclature similar like that, First is give a letter to give to you what type of unit. Look to these pictures, you have different type of units. This first one in the left side, top one is conventional, Mark II, air balance, low profile, reverse, and this portable, and so on, There's different type according to what type you have in the well, Then the first letter gives you what type of units, It indicates for what type of units you are using, conventional or mark. Each letter gives you, indication for what. After that, these units, as I said, is used to transfer or just to convert the rotary motions of the prime mover, motor or whatever, to a reciprocating motion up and down. Meanwhile, reducing the speed, and lifting the floats, then I must have what you call the gear reducers. This gear reducer, what's the capacity of this gear reducer? I use a gear reducer capacity based on what? Based on well floats, based on how much stroke are going up and down, and so on, loads, and stroke going up and down. Then second number of is indicating to the maximum, what maximum rating torque for this gear reducer. And usually this is, reading in 1,000 of pound, what you call, it's rating in 1,000 of inch-pound in the crankshaft of the pumping units. What's mean of crankshaft? This is a crankshaft, and this is a gear reducer. In this one, how much torque is generated, these pumping units, and can be withstand. Each gear reducer, is reducing the speed. It's in 1 time or 2 time or 3 time. The main common, 99% of the gear reducer using for beam pumping units is what we call double reduction gear reducer, reducing the speed inside the gear reducer into stage and so on. Then this unit, how much fluid, how much loads is able to lift, what you call polished road. How much loads will be here in the polished roads, just these units can be lifted up and down, and this usually is measured in hundreds of pounds. Plus how much longer stroke can be lifted, to reciprocating the pump. This is the last number, it's the longest stroke length of the pump. Just to be a little bit more clear, let us to have these numbers on the units and so on, For example, I have the units, this C 1280, D 365, 192. What's that mean for the unit? First, C is a conventional. This type of unit, as you see, is a conventional type. Second, the number 1280, that means torque in the gear reducer. Maximum torque can be in the gear reducer will be this 1280 thousandths inch-pound, maximum torque in this gear reducer. Meanwhile, also, how much load can be lifted by this unit without you have any failures in the equipment, this wire or just bending the walking beam or stresses on this one. Then the maximum load these units can be withstand 36,500 pounds. How much units stroke can go up and down? Stroke, the downhole pumps is 192 inches stroke can go going up and down in this. Really, in the market, since this is being type of pumping unit is limited with a stroke length, and when we increase the stroke length, I have to use a bigger, gear reducers, because this will be, according to the torque, generated more torque. And so the manufacturing currently, is introduced what you call long stroke length, can be reached to more than 375 inches. And this allow not only just, to run the well to produce high volume, because when I use longer rod string, I can produce more volume, because the volume the pump displays is a function of what? Plunger size, pump size, and stroke lengths, how much the stroke length going up and down, plus how the stroke per minute, and so on. Then going up and down, with a longer stroke length, this allow you to produce more. Not only that, also allow you to run the pump at very, very low speeds in order to reduce the friction load, in order to allow you to run in deep wells or run in a deviated wells with a very slow pumping units to extend the running life of the well. As a long stroke, there is some mechanical type, there is some hydraulic type, and even the hydraulic type, there is different type of hydraulics. There is sometimes you can install in the top of the wells, top well head sometimes can be skidded like the bottom one, and so on. Prime mover is the main function of the prime mover is just to generate it, the rotary motions to the pumping unit, either to these conventional types or just beam types, or to the long stroke one. It can be electric motors or can be engine, diesel engine, or whatever type of engine. Electrical motors is one of the main common used type of prime movers for the pumping units, or the reciprocating pumping units. Why? Because it's low maintenance requirement, very high efficiency, as energy cost is much less than to use the engine and feeding with diesel or whatever. No noisy or just very low noisy. You can apply variable speed drive, while you can change the speed in order to, to change the pumping speed for stroke, the pumping units and so on, up and down. And so according to even the prime mover currently, or the motor, there is different type of motor, there is what is like this one, the picture one, what we call the induction electric motor. This is, electrical parts. I will not go a little bit deep on that, but according to the main common used worldwide is the induction motor, and it's specified by the NEMA, is National Electric Manufacturing Association, and each one is say, okay, I use NEMA whatever, NEMA B or NEMA C or NEMA D, or just, combined, whatever. You have each type of motor type. NEMA have a certain type of specification, while you have design, you can selecting a suitable one for your well. But the main common one is used is NEMA D, because it's high slip and, high starting torque and so on can go. Currently in the market, there is really, a new type of motor called permanent magnet motors, while we are, can be, using to reduce the speed, whatever you have. It's usually using in the low torque shaft of the motors, is generating low powers, low consumption of powers, and, it's more efficient than the induction motor. Is just, this is a picture of this. This is a permanent magnet motor of one. Coming to the surface is the wellhead. Is a very simple wellhead. I must have some POP blowout in case I wanted to change any type, something in the top of the well. I have to close the well for this one, because since the rod in the well, I cannot use a valve, I have to use something to close on the rods inside the well and to close the wells. Plus I have something like a flow T to direct the flow to the flow line, and I must have what you call stuffing box. Stuffing box is connecting to the top of the well, which allow the rod string, the polished rod going up and down, meanwhile is preventing the flow to spill around the well, to go out of the well. In this case, the flow only can direct it to the flow line and so on. Coming, just this is a very, very basic, very brief about system component at what we mean, really the reciprocating rod lift system courses or subject need at least, more than 15 lectures or so. However, coming to the rod string or sucker rod bumping system, design, what to consider when I design. Like all the other type of artificial lift, when I design or I need to design the system, I must put in front of me all the possible information, like the well productivity, how much amount fluid I will produce, how much amount fluid will be producing from this well with a certain bottom hole flow pressure, how much fluid will produce if I produce this certain amount of fluid, how much will be the pressure at the pump intake pressure, in order just to allow me to design what will be the suitable depths to run the pump, what's the BVT, pressure, volume, temperature, properties of the fluid, gas volume factors, gas oil ratio, beta oil, formation volume factors, and so on. If this fluid is corrosive, if there is a sand, if this what well completion, what size of tubing I have, what size of casing I have in order to run this completion. At the end, economics way, economics, CAPEX and OPEX I have to run. One of the main important things when we design the artificial lift, whatever, rod lift system, or BCP or ESP you have to start from the bottom. Because I saw a lot of engineers ignore this one. You have to understand that this pump is run at the bottom of the well. Then you don't need to design your pump capability at the fluids and so on based on your standard inflow performance IPR, because standard inflow performance, this is the blue one, curve, is measured the flow rates and the pressure, but these flow rates at the stock tank as the standard condition, 60 degree Fahrenheit and 14.7 psi, but the pump is run at the bottom. If you design, for example, if we said I need to produce 400 barrel per day, in order to produce a 400 barrel per day, you sizing your pump to produce 400 barrel per day. Unfortunately, this pump, at the bottom, the amount of fluid will be higher. Then whatever you reach to the tank will be less than that. However, there is some paper I published about this one in SPE also in details. If you wanted to go in details in that, I can send it to you and so on. Then you have to design based on what? In reservoir barrel per day. This, if you are producing with a pump intake pressure above the bubble point, that means there is no gas at the pump intake. But what happens if there is a gas at pump intake? If there is a gas, then there will be a volume of the gas. And the volume of the gas is occupied the volume of the pump, a part of the pump. And this part of the pump, it will be instead of the pump to displace a full of liquid, no, displace liquid plus some gas. Then the amount of liquid the pump will be displaced will be less. Then the amount of fluid reached to the surface will be less. What I wanted to say here, when you design your system, you need to consider the total reservoir fluid at the pump condition. And yes, the reservoir fluids, at the fluid, you need to consider the formation volume factor. But at the gas, you need to calculate how much free gas at the pump. How much free gas at the pump, how much gas will be venting to the casing, how much volume of gas will be entered to the pump. In this case, you need to design the pump on that. For example, if I said I want to produce 400 barrel per day, then I have to say, yes, 400 barrel per day. If there is no gas, I have to sizing my pump to produce, for example, this amount of fluid. Or if there is a gas, I have to size the pump to produce this size of fluid. For example, if you want to produce about 550 barrel per day at bottom hole flow pressure 200 psi, then you need volume to reach to the tank 550 barrel per day. This is Q. Then what size of pump I have to have this? What volume I have to displace? If there is no gas, you want to size, you need to size the pump to lift 6 barrel per day. Then the pump, what you call pump displacement. The pump downhole, the volume, I cannot say production. Downhole, I say pump displace. How much the pump displace fluid from the bottom of the well to inside the tubing. This is a volume display. If there is no gas, if there is gas and you are not able to vent the gas, all the gas going to the pump, then in order to have 550 barrel reach to the tank, this pump must be displaced inside the tubing over about near to over 550 barrels per day. Then if there is a gas and you're able to eliminate the gas enter to the pump, the volume will be decreased, the volume will decrease until you reach, to, if you are able to eliminate all the gas, then you reach only to 600 barrel per day. Generally speaking, as I said, the pump displacement is a function of what? Speed and plus plunger diameter plus the stroke length. But what stroke length? This pump is running, for example, at the surface, it's 100 inches stroke length. But whatever is reached to the pump is not 100 inches. Then I have what you call effective stroke length. Your stroke length at the surface transfer to the pump via what? Via the rod string. This rod string is what? Is steel. And the steel, it's have a tendency of elongations. Then a part of the steel will be stretches. Then if I have 100 inches in the top, and if assumed due to the load in the steel, this is the stretch is 2 inches, then the net stroke reaches to the pump, it's 100 minus 20 is only 8 inches. Then I use 8 inches. If the stroke per minute is 5, the diameter is, for example, is 2 inches, is 2 square, plus the efficiency. I have two types of efficiency here for the pump. Either it's a mechanical efficiency and volumetric efficiency. All the pump is a mechanical, is a valves, plunger, and so on. For sure, each mechanical system have a certain efficiency for some slippage, some part of it. Then you have to consider the efficiency of the pump. Plus the mechanical efficiency, plus the volumetric, how much amount of gas going to the pump, how much shrinkage of gas going to the pump. Is there is a gas have some foam? Is there is a foam inside the pump? Then two different efficiency should be considered in this. That's V. It's the pump displacement at the bottom. When I want to calculate how much fluid reach to the surface, I have to divide V to the oil formation volume factors and so on. What makes the fluid displaced at the pump different from what we see in the tank? Different things. First of all, is slippage. The plunger, in order to move inside the pump, there is a clearance, there is some space between plunger and barrel. For each stroke, will be some fluid to slip down. I have to calculate and so on. Plus shrinkage, there is a gas in solution, it will be inside the fluid because at the pump size, because the pressure at the pump, the fluid will be under a certain pressure at the pump, but the fluid in the tank will be at the standard conditions. Then when the fluid reaches to the tank, for sure the gas come out of solution, reducing the volume of the fluid. Plus, if there is a foam, this is not in all wells, but there is some wells have foam tendency and so on. Then when I start to design, I should be start from bottom to the top. I should be start from subsurface pump. I have to know what the size of the pump, what type of the pump, what's the material of the pump. Then I have to start with the rod string, what's the configuration rod string, what size, what's the grades, what's the coupling size, is it tapered or just continuous or fiberglass, and so on. Plus the pumping unit, what size of pumping unit, what type of geometry, and some other accessories, sinker bars, some other accessories I have to use, plus the prime mover and so on. I need you to remember what type of forces in the pump, in upstroke and downstroke, in order to understand. And because usually it's a design trial and error. In order to optimize your design, you have to understand what's the forces in the pumping unit in up and down. While you're going upstroke, you have the weight of the rod string, you have the weight of the fluid, you have flow resistance, frictions, all that's we are equal big polished rod load, the load in the upstroke. While we are going down, you are eliminated some of this weight, It's the weight of the float. There is no weight of the float. Then upstroke and downstroke will be different weight. You have to consider this when we design your equipment. Why? Because you have, when you design your equipment, you have to have, you need to have a minimum loads in your system in order to extend your system running life and so on. Then as operating parameters, while the load is increasing, what you call the running life will be decreased. And the load here is structure load and the torque and so on. Then for that reason, you have to optimize, you have to minimize your, you have to produce whatever I need to produce, but with a minimum possible loads in order to extend my running life. And minimum possible cycle. For that reason, we said, if possible, we use long stroke pumping units. I reduce the cyclic, loads, instead to run with 5 strokes per minute, I run with 1 stroke per minute, 2 stroke per minute. Instead for the well to have failure after, for example, 1 year, maybe the well can work on running for 2 years, 3 years, 5 years without rods. When the cycling is increased, that's mean, the load or just the running life will increase, and even the power consumption. There is several software used in the market to sizing the rod string. One of the main common software is called S-Rod. Usually it's S-Rod, this is a screen, what you see from the S-Rod. Also, if in any time, if someone wanna just to have some quick overview about S-Rod, they can, schedule one lecture. This is, just one of the main common software used, just sensitivity analysis for all what's going on the pumping system and rod string and downhole pumps, and you can run different sensitivity analysis for this one. Plus, this can give you about what pumps and configuration and so. And this is just some of the screen of these softwares, and you can analyzing all the data, and even it's built on all the type of units, all the rod string, according to the APIs and so on, and this is just can generate for you more than 10 reports, just to evaluating or your system and so on. The second one is called Roadstar program. Roadstar program is the same like S-Rod also. This can be make some sensitivity analysis and design for you for the system, surface equipment, and downhole equipment. Analyzing rod string, or analyzing pumping unit is the main common device or main common technology used. It's called the dynamometer survey. The dynamometer is the most valuable tools used for analyzing surface and downhole equipment, and it just measures the load at the surface equipment versus position, and based on that, using a certain way of calculation and analysis, is doing some what you call some analysis about surface equipment and downhole equipment. Plus, in order just to evaluate the downhole fluid, where is the fluid in the well, and so there is what we call echo sounding or echometer technique. It can give you how much fluid in the well, if there is a fluid above the pump, if the fluid below the pump, or whatever you have. General also, like the other artificial lift, and this is a slide showing what the list of API and ISO standard for road lift system. Each part of the road lift system, there is certain if API standard you can refer to you in order to know exactly what is the condition, what is the sizing, and so on for that. Just this is all what I have for the time being, and this is a very brief about road lift system and what's going on the road lift. Dr. Ahmed, I received some question, here, like about are there is any limitation of a reciprocating pumping system? For sure, there is a limitation. No type of artificial lift will have no limitation. Yes, road lift system have a limitation. For example, one of the limitation is a float. If I wanted to produce a high volume of the fluid, this system have a certain capability of reduce fluid. And even, with depths, when the depths is increased, the capability of this system to produce high volume will decrease. For example, if I wanted to produce from 10,000 feet, the ability of this system to produce fluid will be not more than 200, 300 barrel per day, Deviation, yes, deviation for sure, even if this system currently is used for deviated wells, but there is some more limitation due to frictions of the rod string to the tubing and so on. Gas, yes, gas there is some limitations. The volumetric efficiency will be decreased, even if there is some, gas pump, gassy pump, and so on. For sure, there is some limitation for this one and so on. Any other questions? You can type your question if you like, I receive another questions here, from one who says, yes, is this system capable to be used in offshore? Offshore is no, because for offshore, this system, required a big space, big space, and usually the offshore is limited with this space and volume on the platform. Even if there is some area, but few worldwide, using a small units, a small thing like in Egypt, in GBC, they are using some small, but it's limited, It's the last choice for artificial lift to be used in offshore operations. Yeah, one more questions here. It's said, how this system is run in horizontal wells. Yes. In horizontal wells, when I said horizontal wells, yes, we run the pump with a certain precautions about two things, here. First things is a rod string. If I have to run this system in horizontal well, I must run with a core rod, continuous rods. The jointed rod is not be suitable for horizontal wells. Second, what type of downhole pump? How can I set the downhole pumps? How can I allow the valves to be open and closed? Then I have to consider this in the design of the pumps and so on. And that can be, yes, can be used, but this could be, yes, sometimes one of the limitation, but according to the technology, as with improvement in the technology currently, the envelope of application between the all type of artificial lift is increased and so on. Any other questions? Yes, someone say about limitation of the gas. Yes, this gas limitation for the gas. Yes, there is some gassy pump, and for the gas, the main problem for the gas, while we are going in the downstroke, if there is a gas in the pump have to be, the troubling valve have to compress the gas below the troubling valve before the troubling valve will be open. If there is a gas, the gas is compressible fluid, then the gas is compressible fluid. That's mean, this is you are losing a part of the pump while we are going downhole. This is a part of the pump will be losing, and this case, the volumetric efficiency will be much less in this case, and so on. There is one more question, say, can we have a class on how the software is used for simulation? Yes, for sure, we can have. I have a license for that, and can I run for you? Really, it's very interested, and maybe even if some of you still studying and we wanted to do some more study, they can use the software, either S-Rod or Roadstar, to do a lot of simulation, a lot of study for that. Yes, we can do that. I received some more question. Will be a fourth lecture about ESP? Yes, will be about ESP, the fourth one, inshallah. Another question, when the artificial lift can be applied on the wells? I mean, what is the main parameter which can indicate that it's time to lift artificially? It's very easy, very simple to say. When you are feel that whatever you are reached to the surface as production, it's not your maximum production, you can have it from the well. For example, if your inflow performance is gift you that, this well is capable to produce at its maximum potential 1,000 barrels per day. And you receive at the surface at the flowing wells is 100 barrels per day. In this case, this is flowing. Yes, you do some optimization first before using artificial lift with nodal analysis in case you have some problem, restriction downhole, you want to reduce any restriction, but still you are not capable to produce your desired production from the well. In this case, you say, yes, they have to run the well artificially. But before also to say I have to run this well artificially, I have to study the reservoir. If I increase the production of reservoir, is this will affect on the reservoir? If there can be created some like water coning or gas coning or whatever, if I increase the drawdown too much and so on. But the volume or the amount of production is reached to the surface is one of the important things can give you indications. There is different things, but this one of the main important things we can have this one. Okay. Any more questions? If no, it's okay. And also, we can schedule, after we finished all our lectures, I can schedule like a panel discussion. I can invite some of expertise from different area worldwide, someone in road string, someone in BCB, in gas lift, in ESP, and so on, and we can have general discussions. You can prepare your questions, and all of us we can answer you, even from different area worldwide, from different country, in order to answer with different language. Any more questions?